Morning, guys. So yesterday we introduced our new model called Electron Configuration. We started seeing some of the limitations on the Bohr model. In fact, those quantized energy levels, those discrete staircase levels, can actually be subdivided. We subdivided them into different floors. We had called them S, P, D, and F kind of rooms. In tomorrow's lesson, I'll actually introduce to you more what those rooms look like. For today, we just want to do a little bit of recap from that model. Basically, electrons, we had three other rules. We basically off-ball. Electrons enter the closest to the nucleus first because they want to be close to the positive as much as they can. As they end up filling in lower shells here, they're going to slowly take in higher and higher shells. So we off-ball lowest energy to highest energy. We followed second rule was Pauli exclusion, which basically said every orbital, every room can only handle a maximum of 2 electrons. Electrons have this property of spin, so they have to be one going in upspin. That's the convention we put in first. And then the other guy going in has to be opposite spin. Outside the element, the electron can switch spin, no problem. It's just by the time it actually enters the room itself, it has to actually be paired up. Then we did Hund's rule, basically, especially when we start getting into the P, which always comes as 3 rooms, D's come in 5, F come in 7 rooms here. Because all those rooms are equal energy, the wording that we used was degenerate, electrons will actually go in one by one, singly, just like we did Bohr model, single, 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 and we only paired it until the second time around. So we're going to rehash some of those rules there as we practice through some electron configuration. So far we've been doing a full configuration, which means I had to build up from hydrogen. Remember, the hard part in this section here is we're not going to be given the energy level diagram, nor given even that summary map here on how do we find, based on the periodic table, what electron is coming up next. Let me just rehash that a little bit, and then we'll just practice through. We'll see a couple shortcuts, and then we'll end off today's lesson with looking at configuration for ions. So, based on a regular periodic table, so I just pulled this from your data booklet here. For the purpose of memory aid, we're going to pull helium. We're going to drag it over here. And what we're going to do is we're going to say these first 2 columns are going to be S block. Electrons going into there are going to be S electrons. The bottom 6 column here for boron over to neon here, these ones here are called P block. They're going to be going into P shells. Your transition metals, when they first show up here, these are called D block. Although we had seen that the S's and P's corresponded really nicely to the row number 1, so this is going to be 1s. Row number 2, this is going to be 2s. Row number 2, so this is going to be 2p. The floor number here matches up really nicely. By the time you get to floor number 4, this one here will be 4s. When the D's first show up here, just remember, it's just a memory aid here, but remember by the time row D actually came about, this one is actually only 3D. Every time D's show up here, they actually come to us as 5 rooms. If every room can hold 2 electrons, in total I'm going to go single, 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 and then I'm going to go pair, 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 pair. In total I'm going to have 10 electrons, which matches exactly the 10 electrons before I enter the P block again. Again, if that's not confusing enough here, let's go down to the 6th row. The 6th row, the first 2 are going to be 6s. At this point, depending on the periodic table that you use, we know the lanthanides and the actinium series are going to be pulled out. Based on our periodic table, though, I would still say the lanthanum and actinium are still in the transition metal block. I would still say these ones here are D electrons. The D electrons are 1 row shorter, so 6s will actually be, this one here would be 5d, this one here would be 6d. But what you'll notice here is between the 57th electrons, 5d, I don't actually come back to get 5d2 until I actually filled up the 14 other electrons. Those ones there are definitely here in F block. F blocks come to us in 7 rooms, and if I have 2 electrons apiece, in total I can actually have 14 electrons. Let's just use that for practice here. Let's see if we can do the configuration. Try without the energy level diagram. Write the full electron configuration. So start from 1s. Let's just try it while I have the periodic table up here. Let's try it for phosphorus, and let's try it for manganese. Okay, not magnesium. Okay, so write the full electron configuration. Definitely, as we get more and more electrons, this list is going to get longer and longer because I have to make a roster of where everyone actually ended up. So let's actually work our way backwards. Phosphorus is sitting right here. Its very last electron is going to be on row number 3. We're in P block, so we're 3p, and we are the 3rd element in, so it's going to be 3p1, 3p2, and 3p3. phosphorus should end with a 3p3. But that only shows me 3 electrons so far. Full configuration says show me all the inside electrons. So imagine starting from hydrogen and helium, right? In total, phosphorus will have 15. Phosphorus will have hydrogen and helium's electron. It will have 1s1, 1s2. 1s2 would have filled that up, so I'm just going to write out 1s2. Then it will have lithium and beryllium's electron, row 2, s block, 2s1, 2s2. I just show you that it's filled. Then the next 6 will be filled up here, 2s1, 2, 3, all the way to 2p6, so that's 2p6. And then we have sodium and magnesium's electron, first element in, 3s1, 3s2, that's filled. So 3s2, 3p I know in total can hold 6 because I have 3 rooms, but phosphorus only has enough electrons for 3 people to go in. They're going to go in single, 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 so 3p3. You can do a double check for yourself here. Not only did we end with the 3p3 that we thought about, if I add up all these superscripts here, they should add up to the total number of electrons because this is a full roster of where all the electrons ended up. Let's do the same for manganese. So manganese here is sitting down here. For manganese, manganese is technically going to be on row number 4. If it were S, it's going to be 4s1, 4s2. But remember, manganese here is a D block. The D's are 1 row shorter. Manganese is 1, 2, 3, 4, 5 elements in. This manganese here should end with a 3d5, right? But full configuration means I still have to start off from hydrogen, helium. You're going to find that although the ordering is going to be the same, remember manganese has a different number of protons. All the energy spacings, all the different staircases, how wide the steps are, they're all specific to each element. We're going to just list the order here. So manganese here would have, again, hydrogen and helium's electrons, so 1s2. It would have lithiums and berylliums, so 2s2. It will have boron over to neons, so that's going to be 2p6. We're going to have sodium and magnesium, that's 3s2. Next one's over, aluminum down to argon, so this is going to be 3p6. Then we actually enter potassium and calcium. This is when the Bohr model sort of breaks down. We get 4s1, 4s2, those are filled. The reason why the Bohr model breaks down is it can't actually show you any inner electrons. D orbitals and f orbitals are considered inner electrons. And in this case, I actually have 5 of them in a 3D room here, 3d5. What I want to introduce to you here, first thing, we did this sort of towards the end of yesterday's class. We're consistent with the Bohr model. So first shell here holds a maximum of 2. Second shell holds a maximum of 8. Third shell, we can say 8. We can say 18. We can say 8 if we're looking at valence electrons. We're going to see this a little bit more in tomorrow's lesson here. The valence orbitals are just as the S's and the P's on the outermost shell. The D's do not count. D's are what are called inner orbitals or inner electrons. Those ones, they are electrons that are around the center, but they don't participate in bonding in the same way the S's and P's do. So if you just count the valence, just the S and the P, so valence S and P, you'll always get 8 per row. If you do count the extra 10 electrons that are inner, we would have 8 or 18. So there's one distinction here. One thing I also want to introduce to you here is sometimes IB especially, even though we sort of went through this, I know the 4s is filled before 3d, so that's why I filled in, I built up lowest energy first. I filled in 4s1, 4s2, and I started filling the 3ds afterwards. The left-right order turns out not to matter. So let's say I had wrote this manganese here, everything the same up to this point, but let's say I had wrote down 3d5 before I wrote 4s2. The reason why I'm saying, so that it would be 3p6 over here, the reason why I'm saying the left-right order doesn't matter, you're going to realize that, oh, the 4s here is actually completely filled. I must have actually entered those rooms first. 3d maxes out at 10. It actually only is up to 5, so I know it's not completely maxed out. Even though I swapped the left and right order, I still know the 4s actually went in first, and then I'm still in the process of filling in my d's. The reason why IB likes doing this left-right order here is to try to put all the energy level 3s together here. So if you look here, now that the 3D is sort of beside it, we now have the 3s, 3p, and 3d. These are all technically energy level 3. These are all technically shell number 3. So left-right order does not matter. We just care sort of which one is added first. We still see that the 4s is added before the 3d is added. Now, like I mentioned here, especially as this is getting longer and longer here, it's going to start getting like more and more gibberish coming up, right? This full roster, if I have 30, 40, 50 electrons or so, it's going to get really, really tedious and also very tiresome, messy. So what we've come up with here is a shortcut. especially because reactions and bonding only really care about the outer shell. Although, yeah, it's neat to know where all the electrons enter in the inner shells, we really only are concerned with the outsidemost. So, what we come up with here is we actually come up with a shortcut. We're actually going to write a shortcut here. They can call the shortcut here the simple electron configuration. Or more commonly, they're going to say, can you write this using core notation? Can you just use a shortcut to actually hide the core, hide the inside, and just tell me, well, how many electrons are in the outermost shell, because those are the ones that do the bonding. In our rule here, so simple electron configuration, what we're going to do is we're actually going to use a noble gas. Noble gases are nice because they have a full shell inside. So use noble gases to hide any inner shells. And all we're going to do is we're going to start off with the noble gas, and then we're just going to tell you what the remaining is. So, for example here, if I did the simple configuration instead of the full configuration, phosphorus here has one shell full, has two shell fulls, doesn't quite have the third shell full just yet. If I want to hide the most, I want to take the noble gas that has two full shells, I want to hide that part there. So the noble gas here with two full shells here is actually neon, row number 2, that would be a 2p6. I'm actually, if I rewrote for phosphorus, phosphorus would actually be whatever neon has, I'll put it in square brackets, so not concentration this time, but it's going to be whatever neon has. That's going to hide these 10 inner electrons, but I still need to put down 3s2 and 3p3 on the outside. So it's like saying, yeah, it has the 10 inner electrons plus these extra 5. These last 5 are going to be the valence electrons. Those are the ones that are of interest. So as you're going through here, because we are going to be using noble gases, with the exception of helium, which ends off with 1s2, that closes the first shell, you'll notice all your other noble gases are in p block. They're always the 6th element in. So this is always going to end in np6, 2p6, 3p6, 4p6. The n can change, but you're looking for the last p6 to close that shell. So if I were doing the manganese again, I'm going to look at, again, helium is an exception. There's a 1s2, but I have a 2p6, I have a 3p6. I haven't quite gotten to my 4p's yet. So in this case here, I probably just want 3 full shells, and then I'm going to tack on the last set of electrons. So the noble gas with 3 full shells here is going to be argon. Argon is row number 3, 3p6. So what I'm going to do, if I redrew manganese here, you will need to be able to practice both full and simple. Of course, for full, they'll probably ask you some of the elements higher up, so you don't have to make such a long list. But simple is a lot more elegant, especially when we get to so many electrons. So manganese, as we shared, this one here is going to be whatever argon has. Argon hides everything up until the 3p6, and now I just leave it with the last column here, last section here, 4s2 and 3d5. So that's called the simple configuration, sort of a shortcut. It hides all those inner shells for you. Right? Let's do one more just for practice. We haven't really introduced the F's yet, so I just want to practice one more with you. Let's say I want to do the simple configuration for hafnium. If I had asked you for the full configuration for hafnium, you'd need to start off from hydrogen, 1s1, 1s2, and build all the way up until 72 electrons. Phew, because we're actually doing core notation, let's just backtrack. Hafnium here is on row number 6. So let's backtrack. Let's figure out what's the noble gas here with actually 5 inner shells that are full. I don't want to be the one to actually write all those. So great. I can say hafnium is everything that xenon has. So actually while I have it, I'm just going to do it on the side here. Hafnium's electron. So we have 72 electrons. If I was asking for the simple configuration, I'd start off with square bracket xenon. I'd say it's everything that xenon has. And then I'm going to tack on the remaining electrons. So xenon already hides 54 electrons. It hides the 1s2 all the way up to 5p6. And then I add in this last row here. I'm going to have 6s. Cesium would be 6s1. Barium 6s2. Those are full. So I'm going to write 6s2. This part here gets a little confusing. The 57th electron is lanthanum's electron. Lanthanum is part of the D block. The Ds are one row shorter, 3D, 4D, 5D. Like we said earlier, lanthanum would now be a 5D1. Now at this point here, usually if you start filling 5Ds, why don't I come back 5D2, 5D3, 5D4? Remember, by the time I get to the really top part of the energy level diagram, you see those energy levels are getting so close together, it's going to start getting a lot of exceptions. Without going through all the details of that there, what we're going to see based on our periodic table, going from element 57 or electron 57, electron 58 actually doesn't enter hafnium shell, it actually enters cerium shell here. And whenever the F blocks first show up, just remember they come in 4. They actually come to us as 7 different rooms. So if I do my Hund's rule again, we go in single, 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 right? Pair, 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 right? There are going to be 7 rooms, 2 apiece, so I'm going to have 14 going across. Imagine, try to build up the electron hafnium. The 58th electron is going to go 4f, 1, 2, 3, 4. It's going to keep building up here until it's actually 4f14. I've completely used up all the lanthanides, and now after electron number 71, now we're back to going electron number 72. Now we're back to the D block, and now we're ready to say again 5D. Wait, do I put 5D2 or do I put 5D1? Remember, the left-right order doesn't matter. So if you know that in this case here, because I finished off the F's and now I'm starting to refill the D's, you can go back and you can start going 5D2, 5D3, 5D4. Just don't put it in both places because then it looks a little confusing. Like, I don't know what that means. So maybe let's just drop it from the beginning, right? I know I'd picked that up first for the lanthanum, but I actually picked up one more so that in total I have 5D2. Again, what I'm alluding to here is if you look at the energy level diagram, the 5Ds, which come to us as 5 rooms, 5Ds and the 4Fs are actually so close in energy. So even though I do want to off-ball, what ends up happening is when I take Lanthanum Selection, I fill in the first 5D1. I then start filling in the Fs, right? They're really close in energy. Until all those Fs here are completely done, now I'm going to come back and start filling in the 5Ds again. Sometimes I don't even come back, so if I wanted, what's the configuration for uranium, right? I'm just going to be F1, F2, F3, and I never actually make it back for my second D electron, so be it. On that note here for uranium, how do I know, let's say core notation, how do I know which noble gas will hide the inner shells? Just look at the element number, element 92, 91, 90, that would have been part of this row, 88, 87, so that means radon, and actually hides the 6 full shells that uranium has. We're going to have basically everything radon has, 7s1, 7s2, you write 7s2, you write 6d1, I pick up the first one for actinium, and then I pick up 1, 2, 3 elements in for uranium. So, just do some more practice with writing the configuration for the atoms. Today I just want to end off with 2 last notes here. One is exceptions. We started seeing a lot of exceptions, especially when these energy levels get to be really close together. There are exceptions that they want you to know. Specifically, they want you to know chromium and copper, because they're going to mainly be asking you configuration for elements 1 through 36. But the exception that we're going to talk about for chromium actually applies to everything underneath it, and as well copper, everything underneath it. Remember, not into the F blocks, because the F block actually belonged they should have been squeezed in the periodic table. It should have been actually a much wider periodic table. So let's go through these exceptions, and then we'll finish off with configuration for ions. So what are the exceptions here? What are the weird ones that they tend to like asking you? For the exceptions here, we're going to start off with copper, and we're going to do chromium as well. Let's see if we can write the full configuration just for practice here. So use your periodic table, not the energy level diagram. Based on what I've told you so far, you should be able to write for me here copper. Looking at where it is on the periodic table, it's in the transition metals here. It's the 9th element in. It's in 3D. It should end in 3D9. Copper should look like that for S2 3D9. Chromium in a similar fashion. I'm just going to do core notation for this. Argon would have actually hidden all 3 inner shells, just like copper does. And then chromium is a couple electrons short from copper. It'd only be 4s2 3d4. That's based on what I've told you so far. What makes them exceptions? In this case here, first thing we started seeing, yeah, we are filling in the S's before we fill in the D's. I just want to show you the electron diagram here again. So this is 4s, this is 3d. We're going to see that 4s and 3d are actually really close in energy. It actually comes back in chapter 3 to talk about why transition metals are multivalent. They have many charges. In this case here, what we're starting to see is, well, copper is actually, out of the 10 places that could be D rooms, I already have 9 out of the 10. Remember, we have this sort of assumption, well, noble gas are stable because they have full shell. They have no desire to actually gain electrons, lose electrons. Same thing happens here. We have 9 out of the 10 available, so if only I could get that one last electron, then I can have a completely filled D shell, then I can gain some stability back. It's just that I didn't have enough people arrive at my hotel. I didn't have enough electrons actually here. So what copper is going to do as an exception, even though energetically the 4s here is actually lower energy, copper does need to pay a little bit to actually promote this electron upwards. But in doing so, it ends up getting that full shell, ends up getting paid back, ends up getting a lot of stability back. So using a money analogy, let's say I say, oh, this takes $10 to move that electron up, but in the amount of stability I get here, stability means lower energy, I'm going to pay you back $100. Would you do it? Well, of course. So although we've been filling it 4s first and then 3d, as an exception, whenever you deal with copper, not even dealing with the ion stuff we do later on, I actually want you to say one of those s electrons got promoted up. In fact, this is just a 4s1, and this one here is a 3d10. Let's see a very similar exception for the chromium. Chromium here is not as close to copper, right? So it's only out of the 5D rooms here, chromium here only has 4 out of 5. In the same way, a full set of D shells gave you more stability. Something about having a half-filled shell, a half-filled set, also makes you stable. So notice out of the 5 rooms, I already have 4 out of 5 because they're all parallel spins. That actually makes me paramagnetic. We'll see that in chapter 3. But again, what's going to happen? I might need to pay a little bit here to get that electron up, but again, having that half-filled shell ends up making you stable. So for those 2 exceptions, I just want you to note down, whenever you see chromium or copper, a filled or a half-filled shell adds stability. So what's going to happen is it will always promote one of its s electrons up to do that. Now, especially as we start going into ions here, we will see other cases. What if I was like a 4s2 3d8? Although it would be true having a 3d10 would make you stable, it turns out the upfront cost for promoting more than one electron is actually too much. So in that case, even though there is that stability for having a full shell, I'm not going to tend to do that. So just for copper and chromium, the reason why I said it applies to the things underneath it as well, molybdenum will have the same configuration of chromium, just one row lower. It would be a 4d4 instead of a 3d4. Or tungsten here would be a 5d4. For all of those, they would take one of their s electrons and decide to promote it up, so it's actually a d5. Copper, everything underneath it, silver, gold, these ones would have been a s2d9, but what's going to happen is it's going to promote one of its s electrons up to actually make it a d10. So just watch out for those 2 elements here. They're a little bit strange to begin with here. Even before we talk about ions, they already have a weird configuration. Now, let's switch over. So far we've been looking at just plain old configuration for atoms. What if we do one final look here at ions? What if they start playing around with the number of electrons? What if more people arrive at your hotel, or you need to take electrons off from your hotel here? How do we do the configuration then? Fortunately, a lot of this is very normal. So the 2 types of charges I can have are going to be anions and cations. I'm going to do anions first. So nonmetals typically gain electrons. They steal electrons. It's like a bunch of electrons arrive at your hotel. As they gain things that are negative, they actually get reduced. That's the terminology. Nonmetals gain electrons to form anions, and anions is the word for a negative ion. In this case here, the rule is quite simple. It's sort of like you have another person arrive at your hotel, you add electrons to the next lowest energy available, right? It's like we off-balled anyways. It's like we want to be close to the nucleus anyways. Oh, you happen to have more people. Oh, just put them into the next spot that you have. So let's just do it as a practice here. Let's start off with oxygen as an atom. So oxygen atom has 8 electrons. Let's do it with the energy level diagram here. We have 1s, we have a 2s, and we have a 2p. Tomorrow we'll come back and we'll actually draw some of these shapes. 8 electrons, so we go and fill in 1s1, 1s2, 2s1, 2s2. We do our Hund's rule, I get 2p4. Now what's going to happen is oxygen is going to get reduced. It's actually going to gain 2 electrons. Now usually when we think about being reduced, right, reduced usually means you lose things, right? In this case here, what's being reduced is actually your charge is being reduced. So I have a 0 charge right now. Because the things I'm actually grabbing are actually negative, my charge, if it were positive, it's going to get closer to 0. In this case, it already was 0, and now it's going to be reduced to -2. So oxygen's normal charge is actually called the oxide -2 ion. And in this case here, basically 2 more people arrive at your hotel. They are also negative. They also want to be close to the nucleus. They can't fit in any of these lower shells here, so they're going to decide to go in. Well, I'm going to fill in that one. I'm going to fill in that one there. And there we go. If I wrote the configuration, it would actually be 1s2, 2s2. In total, it would actually be a 2p6 as opposed to the 2p4 from before. We just added it to a lower shell. What noble gas also has this configuration? Well, the noble gas here, we had said here, noble gases typically end off in p6. The second noble gas here is actually neon. Neon actually has the 10 electrons. I'm not saying oxide is the same as neon, like the same element, but what is the same here is actually isoelectronic. We ran into that word a couple lessons ago here. It's actually isoelectronic with neon. In terms of the electron configuration, oxygen here sure has 8 protons, 8 neutrons. It would have 2 full shells. So here's just regular old oxygen. It's gained 2 extra electrons, so that pairs up, and another electron that pairs up. Because it is charged, we do want to put square brackets around it. The isoelectronic means the same configuration. Neon is a different element. Neon actually has 10 protons. I believe 10 neutrons as well. Also has 2 full shells. We did that question earlier about in terms of the atomic radius. Their size is not going to be the same just because they have 2 full shells. The size would actually depend on how much positive attraction I have in my core. In this case here, because I have more protons in the core, it ends up pulling in the shells in tighter. So even though they are isoelectronic, in this phrasing here, they have the same electron configuration. Exactly the same 10 electrons, but the energy spacings are different. And in this case here, they're actually different distance from the nucleus as well. So anions here, in some sense, more people arrive, you just put them in the next lowest energy spot. We'll end off here with the second type, which are typically, what if I already had the people in the hotel, and what if I need to go up to certain rooms and start pulling people back out? So metals tend to do this. Metals will lose electrons. And in doing so, they're going to form cations. I always want to say cations when I see that word, but cations, right? Cats are positive. So metals lose electrons to form cations. There's a very special order that we remove them in. I want you to just remember this one here. The rule is, as we pull those people out of the hotel, remove electrons in this order. P first, then S, then D, then F. Although the caveat here is it has to be on the outermost shell. Like layers of an onion, you cannot touch any inner layers until all the outer layers have been shed. Usually this is going to be the highest energy layer. There are times that it's not. So let's just do for practice here. Earlier we had done scandium, so let me just redraw that for you. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So that's just scandium as a element, as an atom, neutral. What I'm going to do here is I'm going to try to convert this. Let's make scandium. Let's make this one here, scandium, let's say +2. That's a stable ion that we found within the last maybe 20 years or so, so relatively recent. So scandium +2. This means then, well, I need to pull 2 electrons. Because I'm removing electrons, I'm losing electrons, I'm going to call this actually oxidation. Again, this is sort of flip mentality here. Well, I'm losing stuff, right? Why is my charge getting bigger? The thing that I'm losing is actually negative. So I start off neutral, I start off with 0 charge, I throw away things that are negative. All that's going to happen to me is I'm going to get more and more positive. Just like layers of an onion, you can't touch any inner layers. So you can't just be like, oh yeah, I remember the rule, P, S, D, F. Well, I have P electrons, those come off, those P. No, I can't touch any inner shells until all the outer shells are gone. How do I mark the inner shells? Well, I just mark off the noble gas. Helium here is 2s2, 2p6 here for neon. Argon here is 3p6. I can't touch any of those inner shells. This is something core notation does really well. You can't actually touch anything inside the square bracket until the outer shell is gone. So focusing on that outer shell here, although strangely, we have our energy level, we have our 4s, and we have our 3d like this. Our 4s is 2, 3d 1 like this. Although we were adding, well, 4s is lower energy, the last electron I added was actually a 3d. You might imagine pulling off the 3d first. We're going to learn in tomorrow's lesson the d's, how they're actually shaped to be inner orbitals. the Ds, even though they're energetically higher, especially when we actually pull out electrons, we actually remove the S's first because they are spatially farther away. So what's going to happen here is we don't quite have the 4 P's yet. Then we move on to the S's. Oh, I do have S's. Let's remove 2 of the S's. So now I'm going to get argon's configuration with 3D1. That's the configuration of scandium. That's a nice hint. Transition metals here, if they don't have S electrons, it's probably because they lost the S electrons. Those got pulled off. When scandium forms its normal charge, let's say scandium plus 3, if I remove another electron, yeah, definitely don't have the P's, the S's are already gone, then I'm going to remove the D's, and now we are isoelectronic with argon. So even though scandium itself has d electrons, by the time it becomes charged, it actually has none. We'll come back to that more in the transition metal lesson. So let me leave a couple for you just to practice here. See if you can write the full electron configuration. Write it for aluminum, and then compare it to aluminum plus 3. Right? So start off with just the plain old atom, and then when you remove electrons, see what you get there. Start off with silver, and do Ag+. Careful, silver will have the same exception as copper does. Right? And then just to practice some of the negative ones here, let's just do sulfide, so sulfur as an atom, and let's go sulfur minus 2. And yeah, sure, I'll just leave you with that. All right. So keep practicing through your worksheets. Remember, we won't be given the energy level diagram nor the summary diagram with which orbital is coming up next. You need to know the hints and the ways of reading those, the order from the periodic table. So just practice that, and if you have any questions, just let me know. Thanks, guys.